another young undergraduate with a lot of enthusiasm getting up now. Brian is going to speak on the topic of designing future new alloys. Thank you, Brian.
I should have checked this before I... People have been having trouble with this, haven't they? I've changed the title, I'm afraid, so, it's the prerogative of the speaker, but slightly. Mainly because people have talked about so many interesting things about for the future. So I'm going to talk about multi-component high entropy alloys. Everybody knows that I've been involved with the beginnings of that and its continued activity. And Harry just made a snide comment about it, which I'm resisting rising to the bait of, but we can have the debate later. Okay. So I'm going to go through quite a lot, quite fast. So I want to persuade you that human history is the history of new materials, that all materials are alloys, that there are lots of them, gazillions is a phrase I use, technical term, and that multi-component alloys, multi-component systems are essential to our future and sustainable health, wealth and well-being. So, that's what the meeting is about. So here's my one-slide version of the history of humankind as a history of materials. I'll go through it very quickly. 3 million years ago, humans emerged from Australopithecus. They involved brains. It was because it was the beginning of the Ice Age. And they needed to be better at getting their food. So they needed brains so they could make stone. It's the beginning of the Stone Age as well. They could make flint tools. Flints are found... silicon oxide, lumps of silicon oxide with little bits of calcium oxide, magnesium oxide, which allow you to fracture them to make sharp tips. They're an alloy. Almost 3 million years later, not quite now, but just 12,000 years ago, humankind went through what's often called the biggest revolution ever in our living circumstances. I haven't worked out, I'm nervous about using it. Okay, the agricultural revolution, and instead of being like apes are, hunter-gatherers for food, using those flint tools, they settled down and started farming. They domesticated animals, domesticated plants, and it's because it was the end of the Ice Age, 12,000 years ago. But that wouldn't have happened if we hadn't developed they hadn't developed a new material again, fire clay. Fire clay is an alloy of aluminium and silicon oxides, aluminosilicates. There's loads of them, and some of them are clays. And you need them to have bricks to build houses, and you also need them, even more important, to make pots to store the food. There is no point domesticating cows or whatever it would be, or goats as it probably was rather than cows then, or domesticating plants. And farming them, if you can't store the food, you might as well just go out and be a hunter-gatherer. So it was essential to develop this. This was the key technological development which allowed that to happen. Well, 6,000 years later, people discovered they'd already discovered metals because kilns for the fire clay had been sited on top of occasionally of metal alloys, and the carbon in the wood had smelted. Produced copper and tin and lead and so on. Shiny stuff that was used, very soft, used for decorative purposes only. And then someone discovered if you add a bit of tin to copper, you get a wonderful material, much better than flints or wood tools, because the tin hardens the soft copper. Had to be discovered, and it was discovered. And that led to the development because it needed trade. You had to trade the tin and the copper. It led to governments. It led to civilizations. The first the Mayan civilization in the Americas, the first Chinese civilizations, the most famous one, the pharaohs in Egypt. These civilizations built up on the background of trade, governance and so on, and kings and all that kind of stuff grew up. 4,000 years later, about 1500 BC, they all collapsed. It's called the collapse of the civilizations. And the reason was the Hittites in Turkey had discovered iron. The Iron Age began. The kilns got better quality, and they began to be able to melt iron, which is a higher temperature melting point material. And iron, unlike copper, naturally absorbs the carbon and becomes an automatically alloyed material, iron with a few % carbon. And wrought iron and cast iron is a much better material than bronze for tools and for weapons. So the Hittites won out, and other people. Now the most famous series of new civilizations grew up, and the most famous one is the Romans. The Roman civilization, which came to conquer much of the world, was based on the Iron Age developments. Well, we jump forward to the 18th and 19th century and the Industrial Revolution, which was based on the scientific revolution in the 16th century, and it's the discovery of how to make machinery, how to make engines, how to make industrial production, how to make all the things we now make and use. And it turned lots of people. It's regarded as the second most important change in human existence after the Agricultural Revolution, and it allowed people to move out of starvation, farming, existence into what we now think of as relatively wealthy, well-off existence with disposable income. About 2/3 of the world now has gone through its industrial revolution. Not all, but it began in Britain, in the northern Britain, not far from where I live. But it depended upon a discovery of steels, which Harry was just talking about. They knew about steels, but they didn't know how to make them properly. It wasn't until we had the Bessemer and the open hearth process developed in the mid-19th century, they were able to reduce the carbon down to a fraction of a percent, and it's much more controllable in the kind of way Harry was talking about. It's much more controllable in terms of the mix of strength and ductility, and it allows you to have precision machinery. You can't do that with irons or with bronzes if it comes to that. And we now live in the information revolution, which is dependent on another alloy, microalloyed silicon, and other semiconductors too, but mainly silicon. And, the amazing functionality of our computers and satellite communications and telecommunications and everything and the internet and everything we see going on at the moment. We're living in the third most important revolution in humankind, and it depends upon another material, and it's again an alloy. So I hope I persuaded you in my two first points in the first 5 minutes. I hope I persuaded you that the history of humankind depends upon the development of new materials. You're a pretty good audience for this because you're material scientists and metallurgists, but I try and persuade other people of this who are less attuned to the idea at first. But it's when I look at it, it's absolutely true. And secondly, that all real materials, in fact, all materials, not even real materials, why do I say real? I don't know why I put that in. All materials are actually alloys. Even the purest things we have are alloys. Now, all of this wonderful technology was developed by what I call conventional alloying strategy. And as it says here, that means you take one major component for a main property and you add small-scale alloying additions for secondary properties. I'm going to give you two other very quick examples. Nickel superalloys we heard about in Marty Glicksman's talk this morning. Nickel is for high temperature. When jet engines were first proposed, the famous Griffiths criterion said they'll never fly. We don't have the materials to cope with the temperature. The same year, nickel superalloys were actually patented. First. Very same year he rejected it. It took a while for them to develop. But nickel you have for high temperature. You add a bit of aluminium or titanium for strength. You add a bit of chromium for corrosion and oxidation resistance. So a little bit of those, and then there's some pinches of other things now. But basically there's not very many additional things. Another example is window glass. Completely different example, a ceramic one I like to give. Silicon oxide, cool it quickly, it's amorphous and then it's transparent. But it doesn't work very well. You add a bit of sodium oxide to make the melting point a bit lower, more easy to manufacture, and you add a bit of calcium oxide lime, soda lime glass, because that makes it more stable and it doesn't devitrify when you're using it. But you add a small amount of those things. And there's hundreds of examples I could give you. In the late 70s, early 80s, I began to go around and say to people, I had a bit of a fevered thing about it, why do we never have a multi-component alloying strategy? Why do we never mix large numbers of components in equal or near equal proportions? And we never did that. And I just wondered why. And everyone told me why. They said, it's crazy, it doesn't work. Don't be crazy, Brian, don't do it. Let me just say a little bit more what I mean first. So what occurred to me was, if we think of all the ternary alloys we could possibly make, the ternary systems we could possibly have, we know a lot about the corners of most ternary phase diagrams, but we don't know that much about most of the centers of them. If we have a quaternary diagram, a four-component system, we know again a lot about the corners here, and maybe something on the edges in the binary systems, but we know almost nothing about most quaternaries. If you go to a five-component system, we know almost nothing about any of them. Or we didn't. We're now beginning to know a little bit about some of them, but very few, as I shall show you in a minute. So that's the basic idea, and everyone said, crazy. You're crazy, Brian, don't do that. My research colleagues humoured me and tried to persuade me not to be so foolish. And my research funders said, get out of here, we're not going to give you any money to study this. And my research students said, we want to study something that's going to give me a job when I get finished, not some daft idea. And they had the best argument, to be honest. But I persuaded in the end a more adventurous student, and he was an undergraduate, a young man called Alan Vincent, really nice guy. He was more adventurous, and he really liked the adventure of doing something completely different. And I persuaded him that we should have a go at this. So this was in 1980, and we made up the first ever multi-component alloy, and for many years was the world record. 20 components. Ching, who's in the room, beat me about 3-4 years ago by making a 24-component system, and there's one or two of those have been made now. But anyway, 20-component system, 5% of each of these things, and the first thing we discovered was everybody was dead right. It's rubbish, right? It's loads of complicated components, loads of compounds. Because the reason people didn't if you add alloying, add tin to copper, you start to form a compound which hardens the material. If you add carbon to iron, steel, you start to form a compound cementite or maybe graphite which hardens the material. If you add too much, it hardens it so much it becomes totally brittle. It breaks apart when you make it. And that's what happens if you add too much or you had too many components. But people didn't go far enough, as you shall see in a minute. But the first thing we seemed to discover was everyone was dead right. This is rubbish. It broke up, it cracked up, it was not a good material. But the second thing we discovered within about 3 days was they were wrong. Because this black phase here turns out to be what's now known as the Cantor alloy. I didn't give it the name, so don't criticise me for self-promotion. I think Rob Ritchie is the one that first used the name, but anyway, it's widely used now. And it's this material here. It's a 20% each of chromium, manganese, iron, cobalt, nickel in equal proportions, and it's a perfect single crystal material, single phase material of a face-centered cubic structure. And it was a complete surprise, utterly amazing that should happen. Only one of these 5 components is FCC in its natural form, which is nickel in its room temperature form, and they don't mix with each other fully in solid solution in binary systems. So this was a remarkable surprise. And I'm just going to show you a quick, slightly more pictures of it. This is when it's solidified, it's dendritic, but you can roll it very easily. It's got tremendous ductility. You can roll it and recrystallize it, get beautiful recrystallized annealing twin structures here. When you do an atom probe or other things, you find that it's almost a perfect ideal material. Those atoms are distributed on a face-centered cubic structure almost perfectly ideally. There's almost no detectable at the levels of detection clustering or short-range ordering, anything like that. Well, we published I'll come to that in a second. We published our paper in 2004. For complicated reasons, it took nearly 20 years to publish the paper. And it died a death, just because everyone thought it was a crazy idea. In the first 3 years after its publication, there were 8 citations, probably all by me. Now, that paper, which is almost the last paper, because in 2002 I went off to run universities. I did it almost after I'd stopped being an active researcher. Now, there are literally several thousand papers a year which reference. I get several thousand citations a year to that paper, which is, by the way, for those that don't get too many, that's good. Thank you, God. Anyway, so I get that. So it's been, and there are multi-million-dollar programs in most countries trying to study these materials, and you'll see why in a minute. And despite what Harry said, it's opened up a panoply of enormous range of new possible materials. So that our vista of potential materials, our palette, has been multiplied 1,000,000 and 1,000,000,000,000 billion trillion times over. There are more materials than we even knew existed or even thought about. That's the key thing that we've discovered with this field. But anyway, I went off to run a university, and nothing was happening. But by the end of the 2000s and in the early 2010s, people began to ring me up and say, what are these amazing materials we've discovered? You discovered, Brian. So the Cantor alloy, the one I just showed you, was the first one studied. So this is why people were enthusiastic, because it turns out they have ductilities of 50 to 100%. By the way, there are lots and lots of, in quotes, Cantor alloys, the original one and modified compositions. I'll show you in a minute how many there are. There are millions and millions of them, way more than we've even looked at yet. They all have ductilities of 50 to 100%, even 120%. But they have strengths in the 0.5 to 1 gigapascal, even up to 1.5 gigapascal size. And that beats pretty much anything, as shown here. This is an Ashby map. There's the fracture toughness. I think you were talking about 70 something, Harry, which is here. We're talking. They have about 200 and between 200 and 300 megapascal root meters fracture toughness, which is equivalent, and that's 100% ductility. Very, very the softness of pure copper, like any single phase FCC material. On the other hand, they have the strength, not far off, of the best high strength steels. Not quite as good as the best high strength steels, which are higher. So you can see where the Cantor alloys are, the FCC Cantor alloys. And if you home in onto, that's a comparison with lots of different materials. That's comparing it specifically to steels. These are some of the best steels, and there's the Cantor alloys. So people are excited about that. That's without any microstructural manipulation whatsoever. Just a single phase FCC annealed structure. That's before you start doing clever things like precipitation hardening or grain boundary hardening or you name it. So there's loads of things you can do, and people are doing that. Now, I said there's lots of them. The first book in the subject was published by Murty, Ye and Ranganathan in 2014, and they showed 3 pages of different Cantor alloys, different FCC alloys. They updated the book in 2019, and there's 5 times as many. There's about 10 or 15 pages of different FCC. They're trying to catalogue everything. I'm just finished writing a book on the subject. You cannot now catalogue everything. There's so much that's been done, and a lot of it's been done, the majority of it's been done on these single-phase Cantor alloys. But there's millions of them. There's gazillions of them because there's an enormous region in multi-component phase space of FCC single-phase material. We didn't know it existed, but we now know there's a massive region. But it's not just that. Oh, here's another picture here's a picture of some of the other ones. So it turns out the same thing happens with BCC. There's an enormous range of BCC alloys, which are mostly early transition metal rather than the late transition metal Cantor alloys. These are called Senkoff alloys. The first one was vanadium, niobium, molybdenum, tantalum, tungsten. 5 got stuck in the scientist's imagination as we have to use 5. I don't know why. There's nothing wrong with 6 or 7. But anyway, so people mostly make 5, as you'll see in a second. This is a different 5-component equiatomic alloy. But you can see, again, the beautiful single-phase structure here. But most compound structures, it's the same thing. We now know something like 10 or 20 different or 25 different crystal structures, which you can randomize with multiple components on either on their single lattice or on one of their sublattices. So here is monoaluminide, MAL, with 5 different components. Again, perfect single crystal, incredibly ideal solid solution. Here is that's with the B2 structure, the cesium chloride structure. Here is a rock salt structure. John, we were talking about it. Thank you for reminding me and getting me. I had to go and checking it because in my brain I thought it was fluoride. There is a fluoride version of this, by the way. But rock salt structured, that's the same as sodium chloride. But this is monooxide. This is the first oxide, the first ceramic compound where this was discovered with these things. But you can have 6, 7, 8 components on the cations there. And here is a more complicated sort of perovskite. So you can have, you pick almost any crystal structure we know of in our binary and ternary world, and when you go into multi-component phase space, you find that there's an enormous single-phase region of each of them, all of them. Now the why? Well, it's actually not very difficult to understand, and we knew it almost at the beginning. The main reason, and it's why they're called high-entropy alloys. The structure of material depends upon the free energy of mixing, and the free energy of mixing, when you start to alloy, is dominated by the enthalpy, or basically the energy of interaction between the atoms, and that's a compound-forming tendency in most cases. So compounds that's why you get copper-tin compound, which hardens, which are particles in the bronze that harden it, or cementite, which harden your irons or your steels, and so on and so forth, or nickel aluminide, which hardens your nickel superalloys, etc., etc. And if you keep adding more, you get more compounds, so you end up having it very brittle. But if you add enough, you go over the hump and you start to suppress the compound formation because there's an entropy term, and if you add enough material, then on a single phase, then you get the entropy suppression. So that's why Jinwei Ye, who also independently discovered this whole idea, called them high entropy alloys. Brilliant name, brilliant idea. But it's wrong. Lots of multi-component alloys are not high entropy, but lots of them are. All of these individual single-phase structures are very high entropy, and that's the basic reason that we get these single phases. We get a lot more single phases than we would have expected otherwise. But there's a second reason, which has not been talked about very much, which I put in my book, which is you don't form new multi-component compounds. So, in our binary and ternary world, we've got about several hundred actual crystal structured compounds. You can look them up in Westbrook, whoever it is has compiled the list of them all. And they're all the different crystal structures, we all struggle with when we're students because they get quite complicated, some of them. But in a 3D world, you cannot pack more than 2 or 3 sublattices into a structure. You run out of capability in a 3D world. If you get to 4 or 5, you can't have a structure with 4, 5, 6, 7, 8 different sublattices. So you don't form new. So when you add more components, instead of forming a new compound with a new compound structure, you randomize and you get the entropy suppression effect on the existing compounds. That's what happens. That's why you get this effect. This raises the question, how many materials do we get in this multi-component phase space? Well, it depends upon 2 parameters. One is the number of components you've got to play with, and the second is how different is a material before it's a different material. It's called the specification, which was invented for patenting purposes, so that when your supplier gives you the wrong material, you can sue them. So that kind of thing. So you have to know what the specification is. How different can it be when you've got the right material? So let's call that x%, which means there's 100 over x, n composition values for each component, and the total number of alloys is given, if you've got C components, and x and n is given by this number. It's a bit of combinatorial maths. How many components have we got? We've got 118 elements. If you take out all the radioactive ones, take out all the noble gases, you end up with 80. But let's be hyper-conservative and say that the most well-known ones, there's probably 60. What's the specification? Most engineering materials are specified to 0.1%. We know as material scientists, you change the composition by that much, you can change the material properties pretty dramatically. But often, it's specified to 0.01%. The highest strength steels and the best semiconductors are specified sometimes to parts per million. But let's take 0.1%. A reason I take 60 and 0.1%, that's pretty conservative, and it turns out the answer is there's 10 to the 100 different materials. You can think of it as a 60-pointed polyhedron in hyperdimensional space, the equivalent of the tetrahedron and the triangle I showed you before, and there's a point every 1,000 points along each axis, because there's 1,000 different composition points to have different materials along each axis. 10 to the 100. If we're absolutely totally hyperconservative and say we're going to have 1% specification, there's still 10 to the 45. Don't worry, these are all such massive numbers. All you can say is, and I've given you the word already, there's gazillions of them. Every time I look at this, I think to myself, wow, it's even bigger than I thought before. To make the point, the number of atoms in the galaxy is estimated to be 10 to the 80. That's the number of atoms in the galaxy. So think of multi-component phase space as being a 60-cornered hyperpolyhedron with 1,000 materials in each dimension. It's utterly enormous, and there's gigantic regions of single phases of every crystal structure we know, and between those, there's multi-phase structures, like the first picture we got, of our 20-component material, which have got multiple, not high entropy, fixed stoichiometry compounds, which are very brittle. And they've hardly been looked at. People have ignored those. They've ignored most of the whole space. Well, there's a lot to look at. So the question is, how are we going to look at all this stuff? So there are different strategies. So the first strategy, which I've already shown you, which we had, is what's got the grand title. I learned this much later, the Edisonian method. I call it trial and error, which is a bit of a more humdrum way of putting it. Edison believed in trial and error, by the way. But we can be intermediate and call it careful scientific experimentation. The scientific revolution in the 16th century depended upon the notion of discovery. You go out and find. And there's loads to find. The good news for all our material scientists of the future is there's a gazillion more materials to find with a gazillion more interesting properties. Right, I'm going to move very quickly. So, people have tried to use extended Hume-Rothery rules. It turns out that it doesn't work. It does work, but it doesn't work any better than it works in binary and ternary systems. Basically, there are 2 effects, mechanical strain and an electronic strain. And those 2 give you a rough decision about whether things will dissolve in each other or not, but not much more than that. It works sometimes, it doesn't work other times. People have constructed multiple parameters, and it doesn't do much better. So there's been loads of papers published on it, which haven't really got much better than saying, well, the human rules work roughly. Thermodynamic modelers came along and said, well, we can do it all by thermodynamic modeling. They can't. The parameters you need to do thermodynamic modeling, anything beyond a binary or ternary system, are so complicated, unless you make the material in the first place, you don't have the parameters to be able to predict it. So you can't predict it before you've made the material, which is what people are hoping to do, as a way of charting this enormous region. And then the atomistic modelers said, we can do it all with ab initio modeling. No, you can't. You can't do it. Ab initio modeling is wonderful, but you can't do proper ab initio modeling with more than about 20 or 30 atoms. And if you want to look at a random structure, there are two ways of doing it. You either have to have a mean field assumption, and that washes out all the difference of the different components, which I will show you is important in a minute. Or you have what's called a supercell, where you randomize it, and you again wash out all the differences. So it turns out that it occasionally gives you the right answer, and it occasionally doesn't give you the right answer for these materials. And the machine learning guys came along and said, well, statistical inference, that's a great way of finding patterns and telling you what's going on without even needing to have any theories. Well, yes, that's good. If you've got a lot of data and in this field, you get 90 to 95% accuracy on the training data. When you put it into the trial data, it tends to go down to 80 to 85%. But that's data points right in the middle of where you've already got loads of other data points. It's interpolation. If you want to extrapolate to somewhere else, forget it. You can't even do it. So the truth is that there's no alternative to experimentation. Supported by these, I don't want to overdo it. Those are useful methods. Now, I wanted to talk very quickly in the last 2 or 3 minutes about the local structures. So here is a schematic of a 10-component system. And of course, unlike pure copper or pure iron or something, or pure silicon, the properties at each point are different because there's 10 different atoms. But it's more complicated than that, because around each C atom, the properties depend upon the local near neighbours. So this C atom here has different properties to this C atom because its near neighbours are different. And the first and second near neighbours have an effect. So we ask ourselves, how many local structures are there? Well, the number of local atomic structures is the number of ways of distributing C components, in a 5-component system that would be 5, across the number of an atom and its first and second near neighbours, which is 19 atoms for FCC. The answer is C to the n, which if you do it, calculate it, for the Cantor alloy 5-component system is 20 trillion. There are 20 trillion different local structures. To put it crudely, you need a grain size of 30 micron to sample all of the different structures there are. So, put it another way, if you have grain sizes smaller than 30 microns, each grain could have a different property. It's like each grain is like a big macromolecule in these materials. People have not made as much of this as they ought to have done, because I'm going to go on and show you well, first of all, let's see if it's right. By the way, I didn't point out, but because of that variation, you get local strains in the lattice, and you get both mechanical and electronic. As you move around the lattice over 30 microns, the strain is going up and down, both mechanical and electronic. So here's the Cantor alloy, 5 components. They differ by about 2.5%. That's a big strain at maximum, you'd expect. And it turns out that if you do neutron diffraction or synchrotron X-ray diffraction, that gives 2 picometers. This gives 5 picometers. So that gives it's the right phrase. It was 3 picometers was the prediction from the Goldschmidt radii, which is not a perfect prediction. In the BCC alloys, by the way, it's a bit larger. It's about 7 or 8%. But these are big strains, 7 or 8 picometers, which is not far off that in percent. So these are big strains in these materials over large regions. But let's think about the local structures. Let's think about vacancies. The same thing, except the vacancy is the same always. Around a vacancy, you've got 18 first or second near neighbours in FCC, 14 in BCC. This is, again, not far off 20 trillion different vacancy structures. Okay? That means that when an atom a vacancy is hopping around, it's going through a complicated energy variation. The vacancy formation energy and the vacancy migration energy is varying from point to point over that 30 microns. That means that the vacancy gets stuck in a certain place where there's a low and it gets stuck and it doesn't move around so much, and so the diffusion rates go down. You can't guarantee exactly which alloys they'll go down or by how much, but the only really good studies are by tracer diffusion, and here you can see about an order of magnitude reduction compared to a single, simpler FCC material. Dislocations, same thing. Along the core of a dislocation, the structure is varying from point to point. In fact, with a 10 to the 10 per square meter dislocation density and a anneal dislocation density, 20 different clusters in a 5-component FCC alloy needs 6 kilometers of dislocation length to sample every possible structure, which with that anneal needs a grain size of 8 millimeters to contain that number of different things in the dislocation. And that's why the strength is so high. So because it's a simple FCC structure, the way that the dislocations move under strength, this looks just like a pure copper or pure gold. You get dislocation growth and multiplication and piling up in exactly the same way as you get in pure FCC gold or pure FCC copper, but it happens at a much higher strength level because the strains associated with along those dislocation cores are resisting the motion, and it gets very jerky. And I'll just show you that quickly. So the theory of that is complicated, but it fits extremely well with experiments, and it's been done in a whole series of cases. Here is some pictures. The stacking fault energy is low, so you get a separation of partials here. But the separation of partial varies as you go along the dislocation line because the structures is varying as you go along it. Here is some modeling to show, here is the two partials, and as it's put under stress, it moves, and it moves in this very jerky way. And it needs a high stress to move it past every atom is a center of strain and a center of restriction on the motion. I'm nearly finished. Just quickly then, the last slide, properties and uses of these materials. Well, the Cantor alloys have the best low temperature and properties and room temperature properties in terms of fracture strength, fracture resistance and strength of pretty much any known material. You can argue it depends which you prefer best. They're particularly good on their ductility and fracture resistance and at very high strength. The Senkoff alloys turn out to have absolutely outstanding high temperature strength. There's been almost no optimization of these materials. People are now trying to do all the microstructural manipulation, composition changes, all that has hardly been touched. So there's way to go yet on improving these materials, so let's wait and see where we get to. They've got excellent corrosion radiation damage resistance, better than stainless steels. You can tune the properties very often by changing the composition. And the last thing I want to point out is about recycling and reuse. So we've got approaching 5,000 different grades of steel. We've got approaching 500 different grades of aluminium, a bit fewer than those. If we're going to have sustainable, recyclable, reusable materials, we've got to have fewer grades, and the grades have got to be usable in multiple circumstances, and we're going to have, therefore, more generic alloy compositions to provide the different range of properties, and they've got to be resilient to pickup of impurity. That all points at multi-component materials. So, human history is the history of new materials. All materials are alloys. There's a lot of them. There's some wonderful new materials for material scientists to go and find, and we need generic alloys for our recycling. Thank you.
Aren't they a bit expensive?
Not necessarily. Depends which ones you make. They're not likely to be significantly more expensive than the wonderful single crystal directionally solidified alloys we just heard about, which were so incredibly transformative, which, by the way, I agree they were. So let me respond to exactly what Harry said. Right? He said graphene, ludicrously specific, one component, fantastic one property, made in tiny little proportions, very difficult to scale up. At the other end, a steel where we've tweaked the composition. There's a lot of stuff in the middle is all I will say. And there's a lot of cases where we use stuff in the middle. And one of the greatest cases is directionally solidified nickel superalloys. So I rest my case. I could give you 100 other examples. Yes, we're not going to be making these multiple component materials in order to replace bridge steel. I don't think, but maybe. By the way, I don't rule anything out, because the history of alloy development, by that history of all sciences, whenever someone says you can't do it, and I've learned it now to my gain. They said you can't do it. You can't make multi-component. You can. They said the sun went round the Earth, and they were wrong. You know, science is littered with people saying you can't do this. This must be true, and then we find actually you're wrong.
Marty, last question.
So there's plenty of great materials to find, is the point, and you know the cost will be a key component, obviously, of the actual application of anyone.
Brian, what about the electrical properties?
Yeah.
Could you say a few words about it?
Yeah. So it's very interesting because I've just finished my book, and it's actually the last bit. I left it to the end because I hadn't got it straight in my mind, the electrical properties. I've got it pretty straight now. So when you solve your wave equation, to look at the electrical structure of take a metal, the same would be true for a semiconductor or indeed a ceramic. An insulator. When you solve your wave equation, you may remember that when you have a single crystal, you use the Bloch theorem to develop a set of Bloch waves. And the reason you do that is because the wave function has a series of solutions, but it's very complicated to find them. And if you have a crystal, the regularity allows you to transfer to do a transfer of the wave equation solutions into a set of plane wave solutions, which is a simpler set of solutions. So it allows you to solve the problem. So, and our Brillouin zone theory is all built up on that basis, and our electronic band structure theory, which we see lots of pictures of, and is very important. That's all built up on the basis of Bloch waves. Because the lattice is varying all the time, the Bloch wave theorem technically stops working. They're not that regular. But what really happens is it kind of gets smeared out at the edges. So what happens is your bands are smeared at the edges. And at the Fermi level, the electronic states are smeared at the edges. What's really happening is point to point, you've got different things going on. So, at one point, you've got a little bit of charge transfer into the bands, into the electronic system. Another place, you've got a little bit of charge removal. At some place, you've got a bit of mechanical strain so that the shape of the Brillouin zone has changed to somewhere else. You can't really create a Brillouin zone with a set of plane waves. But a way of thinking about it is either at the point level, a little bit of charge transfer and a little bit of change of electronic structure here, at every point. And another way of thinking about it is a smearing of the average. That produces scattering. So you get low electrical conductivity for a metal. They're metallic, they conduct, but their conductivity is reduced. Their thermal conductivity is reduced as well because it scatters the electron scattering of the thermal transmission gets reduced as well. And so they're actually of great interest for thermal barriers. They've got great thermal barrier properties, with the metallic. So that's the rough answer.